Good afternoon, everyone. My name is Chien-Jen Tang from the Department of Photonics, Feng University, Taiwan. Thanks for SVC to invite me to have this talk. I'm glad to have the opportunity to present my recent research on development of reactive HiPIMS process for optical coatings. I hope that this talk can provide useful information of high-quality optical thin films deposited by reactive HiPIMS technique. First, I will cover the application of optical coatings, what properties of thin films we care about, and what deposition method we can choose from. Second, I will discuss functional optical coatings for high abrasion resistance, and how to stable control reactive HiPIMS process, and to compare the thin film properties for different pulsed power or plasma-assisted reactive magnetron sputtering process. Finally, I will make a brief summary. Optical coatings are mainly prepared by ion-assisted electron beam evaporation, magnetron sputtering, and ion beam sputtering. Optical coatings can be applied to optics and displays of optical components, and applications on semiconductor industry such as EUV mirrors. Application of militaries. Coatings can be used for mid-infrared or far-infrared optics or head-up displays. Applications of commercial electronics, for example, narrowband pulse filter used to Face ID or LiDAR in iPhone. Solar absorption coatings, anti-reflect coatings, and low-E coatings were applied to solar thermal collectors, solar panels, and glazing glass respectively. Some anti-refractive coatings on metal can be applied on decoration and anti-counterfeiting, and important for some science research, for example, low mechanical loss coating in advanced LIGO. A dielectric film coating on a substrate, and the incident medium also a dielectric material. The film will support multiple beam interference as shown in the left figure. Let the film be very thin so that the reflection is exactly what we would expect from an uncoated surface. Now let the thickness of the film be increased by a number of quarter wave thick. The phase condition is perturbed to a maximum extent so that reflection changes significantly. Let the thickness of the film be increased by 1/2 wave over a whole number of half waves. The interference condition is equivalent to that of the finished thin layer. Here's the reflectance of the uncoated substrate. Most optical coatings have more than one layer. Some have more than hundreds of layers. It can be assembled based on stacking of quarter wave and half wave layers. The interference calculations in such case can be very complicated and are usually carried out on this day by computer. For a simple example, anti-reflective coatings made of niobium pentoxide and silicon dioxide films. The physical thickness of each layer is shown in the figure. The reflectance spectrum of each layer is shown in the figure. If the thickness error of each layer is about 1%, the reflection spectrum of the anti-reflective coating changes may not be suitable for application. This means that thickness errors must be precisely controlled to below 1 nanometer or less. The physical properties of the optical film needed are dense, low loss, uniform, low residual stress, or others. A dense film means a high pigment density to produce a high index of reflection. Thin film absorption is caused by the film of non-stoichiometric compounds or light scattering from surface roughness, grain, or current structures. An inhomogeneous film refers to a change in refractive index as the film thickness grows. It would be difficult to get the practical spectrum of the multilayer coatings to be close to the design spectrum. Low residual stress will have lower substrate deformation to avoid film peeling or cracking. Other required properties of optical thin films may be high hardness, high abrasion resistance, high laser damage threshold, or specific crystal structure, and so on. Coatings are usually manufactured by condensation of a suitable vapor and vacuum. The different processes vary in the way in which the vapor is produced by thermal evaporation and sputtering. Disadvantages of the IED process are the low kinetic energy of the particle, resulting in low film pigment density, non-stoichiometric nitride or carbide films, and the poor adhesion of the film to the substrate. Disadvantages of the IBSD process are low deposition rate, low production yield, and high residual stress in the film. Optical coatings are usually prepared by reactive magnetron sputtering, but the disadvantages are slow oxide and nitride deposition rate, arcing problems, particle contamination, and high residual stress in the film. The above disadvantages can be solved by plasma-assisted reactive magnetron sputtering process. Several types of power sources are available for plasma-assisted reactive magnetron sputtering, including DC, pulse DC, medium frequency, or bipolar, and HiPIMS respectively. Commercial products with anti-reflect coatings need highly wear resistance. However, there are fewer research studies on abrasion resistance properties of different optical coatings or different substrates. In this table, list of hardness of films commonly utilized in anti-reflective coatings prepared by magnetron sputtering. The silicon nitride and the aluminum nitride films have a higher hardness level than other materials. It has benefit of improving the hardness of anti-reflect coatings. This figure shows the noob hardness of substrates. The sapphire is highest hardness, which is harder than 18 gigapar in noob hardness. The hardness of gray substrate are about 6 gigapar, but the thinness of the hard coatings and the lack of loss support capability provided by the low hardness substrate will show a low surface durability for abrasion resistance. To provide high hardness and dense film, the reactive HiPIMS process will provide high kinetic energy of the sputtering adaptants. The arcing phenomenon occurred on reactive sputtering process when poison layer forming on target surface or near crystal region. The deep oscillation magnetron sputtering could be used to avoid arcing problem. for low hardness substrate. To propose a new anti-reflective coating design concept was used to increase the thickness of high hardness layer in anti-structure. Optimize process parameters for HiPIMS and the DOMS of aluminum nitride, aluminum oxide, and silicon dioxide coatings listed in the table. HiPIMS for aluminum nitride has a higher peak power density than other processes. The discharge voltage and the current waveform of HiPIMS and the DOMS recorded for aluminum nitride and aluminum oxide as shown in these two figures. The structural schematic of the equivalent absorption layer anti-reflective coating with aluminum nitride by HiPIMS, aluminum oxide and silicon dioxide by DOMS and named HiPIMS ELRC is shown in this figure. This figure is the admittance diagram. The measured reflectance curve coincides quite well with that of the theoretical design for the HiPIMS ELRC. The total physical thickness is about 1 micrometer. Physical thickness of aluminum nitride, aluminum oxide, and the silicon dioxide film were about 830 nanometer, 163 nanometer, and 15 nanometer respectively. The ratio of thickness of aluminum nitride divided by thickness of silicon dioxide and aluminum oxide is about 4.7 times. For oscillating sand abrasion test, the bare test according to STM F735 was standard chlorosilicate sand for 600 cycles and the white current sand for 6,750 cycles. The grain size of gray chlorosilicate sand and the white current sand were about 1.7 to 4.0 millimeter and 360 to 600 micrometer. General design for 4-layer anti-reflective coatings by pulsed DC magnetron sputtering made with niobium pentoxide and silicon dioxide, or silicon nitride and silicon oxide, or made with aluminum nitride and silicon dioxide, and by HiPIMS process made with aluminum nitride and silicon dioxide. After bare test, the hash value were about 10.4%, 7.6%, 4.2%, and 4.0% respectively. For pulsed DC magnetron sputtering ELRC, HiPIMS ELRC, and HiPIMS ELRC with aluminum oxide top layer, the hash value were about 3.9%, 1.3%, and 1.3% respectively. The ELRC by HiPIMS process is lowest hash compared to other design or other processes. For large grain size of abrasive medium, put scratch and remove the coating structure to result in large change in reflectance and hash after abrasion test. The fine abrasive medium was only abrasion the top layer of coating structure, therefore just slightly change in reflectance and hash after abrasion test. For anti-reflective coating on sapphire for abrasion test with chlorosilicate sand, the coating has smaller change in hash value than gray substrate. Comparison of ELRC by pulsed DC magnetron sputtering made with niobium pentoxide and silicon dioxide, or by HiPIMS made with aluminum nitride and silicon dioxide after bare test with standard chlorosilicate sand, as shown in these two figures. The hardness of niobium pentoxide was lower than aluminum nitride. Most of the damage of cutting plunging operation medium transferred to the sample surface and the microcracker were observed on SEM image, and less surface damage were observed on HiPIMS ELIC by aluminum nitride and silicon dioxide fins. We try to determine the change of reflectance spectra of ELICs after bare test by the essential macro software. We decrease design layer from layer 13 to layer 9 on gray substrate. The reflectance was increased as decrease in number of layers, as shown in this figure. The reflectance of ELIC made with aluminum nitride and silicon dioxide fins was changed to 3%. It has higher hardness to resist the abrasion of silica sand. For simulation, the surface damage might be dipped to 2 layers, from layer 13 to layer 12. But for ELIC made by niobium pentoxide and silicon dioxide fins has large damage that might be dipped to 5 layers, from layer 13 to layer 9. Compare of ELIC by pulse DC mechanism sputtering made with niobium pentoxide and silicon dioxide, and by HiPIMS made with aluminum nitride and silicon dioxide after bare test with current sand, as shown in these two figures. Anomalous surface damage of cutting, plunging, abrasion, median adhesion, and microcrack were observed on SEM image for ELIC made by niobium pentoxide and silicon dioxide. The SEM image clearly observed that the ELIC made by aluminum nitride and silicon dioxide had only slightly surface damage compared to the ELIC by niobium pentoxide and silicon dioxide fins. We also simulated the change of reflectance spectrum of ELIC after bare test with current sand by the essential macro software. The fine current sand for abrasion resistance test is similar to surface grinding. The top layer thickness was changed from 16 nanometer to 2 nanometer after bare test. The fin thickness of top layer was grained about 14 nanometer. The reactive HiPIMS process suffers from plasma instability, high arcing issue, and slow oxide or nitride deposition rate. It caused by dielectric compound layer forming on target surface and high discharge voltage to break down dielectric layer. This problem might be solved by 3 ways of closed-loop control process for hysteresis loop at a range of transition mode, or change the sputtering powers to high-frequency mode, or using 2-stage plasma-assisted reactive mechanism sputtering process. We have successfully to fabricate a gradient index lookup filter by reactive pulse DC magnetron sputtering process with PID closed-loop sputtering voltage control. These two measured transmittance curve coincide quite well with that of the cylindrical designs. We also try to prepare optical multilayer coatings by reactive HiPIMS process. For aluminum oxide nitride fins by reactive HiPIMS process, aluminum spectrum light during HiPIMS process as segmental oxygen flow rate in ramped from 0 to 1.6 SCCM. For example, the intensity of aluminum emission line was used to determine the PID parameters as oxygen flow rate in range of 0.8 to 1.2 SCCM by Ziegler-Nichols method. Refractive index and the deposition rate versus intensity of aluminum emission line as shown in these two figures. The layer numbers and the physical thickness of Lookup filter were 301 layers and 3.2 micrometer, respectively, as shown in the figure. Layer 1 to 59 and layer 242 to 301 are appartization layers. The refractive index in layers 60 to 241 were distributed in 18 cycles quasi-sine form. The refractive index and the thickness were controlled by PID plasma emission monitoring, as shown in this figure. But these two figures showed more arcing. The experimental result shows the center wavelength and the bandwidth were 393 nanometer and 35 nanometer, respectively. These values were close to the theoretical design, so that the PID closed-loop PEM system can be used to control the process. The experimental transmittance of sideband and the starband were lower and higher than transmittance spectrum of theoretical design. However, the occurrence of arcing and the ejection of melting macroparticle can be resolved. It would be result in light scattering from this surface defect. The reactive HiPIMS process for aluminum oxide fins was not suitable for directly use in optical coatings. So another solution in 1989, Oakley Incorporation applied a pattern of the metamor sputtering process. Nowadays, several companies or research institutes continue to develop the mass production equipment and use it for advanced optical coatings. For example, Synchron, Alvec, and Optical in Japan, and Dayong in Taiwan, Fraunhofer IST, and Bullerlibel Optics in Germany, and Avatec in Switzerland. In my lab, we have developed a homemade plasma-assisted reactive magnetron sputtering. The sputtering power could be modulated as DC, pulse DC HiPIMS, super-impulsed HiPIMS adding medium frequency, deep oscillating magnetron sputtering, and the plasma-assisted reactive magnetron sputtering process. A home-built ICP system is used as plasma assist source for compound reaction. A self-development hybrid broadband and single wavelength optical monitoring system was used to monitor the optical signals. The parameters of HiPIMS, super-impulsed HiPIMS adding medium frequency power, DOMS, and pulse DC magnetron sputtering are listed in the table. The on-off time and the power of pulse superimpulse in HiPIMS are listed in the table. The discharge voltage and the current waveform of HiPIMS, superimpulsed HiPIMS adding medium frequency power, and deep oscillating magnetron sputtering recorded for aluminum nitride and aluminum oxide as shown in these three figures. The parameters of plasma-assisted reactive HiPIMS and plasma-assisted reactive pulse DC magnetron sputtering listed in the table. The metallic film was sputtering from an aluminum target and oxidation or nitridation in region of ICP plasma to avoid target poisoning. The arcing count of aluminum oxide film deposited by HiPIMS and the superimposed HiPIMS process increased with deposition time, and no arcing count were observed in other processes. The transmittance spectrum of aluminum nitride and aluminum oxide film prepared by different processes were shown in these two figures. The high inhomogeneity of aluminum nitride films is due to the aluminum nitride film structure having a C-axis that were perpendicular and parallel to the crystallinity of the substrate. The aluminum nitride film by superimposed HiPIMS adding medium frequency power, deep oscillating magnetron sputtering, and pulse DC magnetron sputtering were slightly inhomogeneous, which crystal structure were influenced by kinetic energy of this deposition process. Low kinetic energy changed the crystal structure to the 100 plane as pulse DC magnetron sputtering and deep oscillating magnetron sputtering only formed the peak of aluminum nitride crystallization in 100 plane. The homogeneous aluminum nitride thin film of plasma-assisted reactive HiPIMS and plasma-assisted reactive pulse DC magnetron sputtering are due to the crystal structure of aluminum nitride thin films exhibiting only strong 002 diffraction peak. All aluminum oxide films were amorphous prepared by all processes. Almost the aluminum oxide films are homogeneous by different process methods, except for the film prepared by HiPIMS process, which is caused by more arcing. Optical constants and the physical properties of aluminum nitride and the aluminum oxide films prepared by different processes as shown in this figure. The aluminum nitride film deposited by plasma-assisted reactive HiPIMS process has higher refractive index, more homogeneous, and low surface roughness and higher deposition rate. The aluminum nitride and the aluminum oxide films were deposited by pulsed DC magnetron sputtering with lowest extinction coefficient and the lowest residual stress. The plasma-assisted reactive HiPIMS process was a selection from the comprehensive consideration of stable process, homogeneity, low surface roughness, low residual stress, high deposition rate, and a high packing density, and the extinction coefficient about 10 to the negative fourth power. 3-notch filter alternative stack aluminum nitride and aluminum oxide film were prepared by HiPIMS, deep oscillating magnetron sputtering, and plasma-assisted reactive HiPIMS respectively. The vertical thickness of 3-notch filters were shown in the figure. The transmittance spectra was shown in the figure. The transmittance of sideband of notch filter by HiPIMS was lower than deep oscillating magnetron sputtering and plasma-assisted reactive HiPIMS. The image of microscope of notch filter by HiPIMS shows more large particles. It could be caused by the occurrence of arcing and the ejection of molten macroparticles from poison target. The notch filter by plasma-assisted reactive HiPIMS shows the clearest surface to compare with notch filter by deep oscillating magnetron sputtering process. The areas prepared by reactive HiPIMS and the DLMS process could be used for high ablation resistance anti-reflective coatings. The DLMS and the plasma-assisted reactive HiPIMS process is used to stable and to avoid arcing for deposition of aluminum oxide fins. The physical properties of fins could be modulated by different pulsed and plasma-assisted processes, and could have more wide applications on functional optical coatings. The plasma-assisted reactive HiPIMS is a suitable process for deposition of high-quality optical aluminum nitride and aluminum oxide fins. Finally, we own a special thanks for Ministry of Science and Technology of Taiwan and the Dayong Corporation for financial support. And last, thanks for your attention. If you have any questions, please feel free to let me know. This is my contact information. Thanks again.